Labas rytas, good morning. I'm Jonas Žmuidzinas, Professor of Physics at Caltech, and it's my great pleasure and honor to introduce this morning's invited speaker, Dr. Charles Elachi, Emeritus Professor of Electrical Engineering and Planetary Science at Caltech. Born and raised in Lebanon, Charles completed his undergraduate education in physics in 1968 in France at the Joseph Fourier University in Grenoble, also receiving a master's degree in engineering. And then he came to California to attend graduate school at Caltech and received his PhD just 3 years later at age 24, 1971, writing a thesis on electrodynamics in periodic media. A few years later, in 1976, Charles expanded on his thesis and published a paper in the IEEE proceedings on the same topic. And this paper continues to be highly cited today, and it connects to various contemporary topics such as metamaterials, diffraction gratings, phononic crystals, and so on. Charles's connection to JPL and NASA started when he was a graduate student at Caltech. As some of you may know, JPL was started by Caltech students in the 1930s, so 90 years ago, who were playing with rockets. And Caltech has managed JPL for NASA ever since NASA was created by President Eisenhower in the late 1950s, shortly after Sputnik. So even before completing his PhD, Charles was already working with JPL. He was working with a group that was working on radar instruments for space, imaging radars, also known as synthetic aperture radars. This is a technology that goes back to the 1950s. This group was working on applying them for space. One of the early goals for this JPL group was to develop a radar that would go on a spacecraft orbiting Venus, to use the radar to penetrate the clouds on Venus and to be able to map the surface. And this concept, this idea, is something that Charles worked on shortly after he got to JPL in the early 1970s. Eventually, this mission did happen with the launch of the Magellan spacecraft in 1989. And in fact, this kind of work continues to go on to this day. JPL scientists last year used data from the Magellan mission to discover an active volcano on Venus. This was work in preparation for JPL's next mission to Venus called Veritas. But that was a long time to wait, several decades, and Charles and his colleagues weren't prepared to wait to go to Venus to fly these radars, so they started doing Earth orbiting missions, starting with CSAT in 1978, and then a series of radar missions on the space shuttle. And Charles led these projects, and the first of these on the space shuttle, called Sur-A, very famously discovered ancient riverbeds and other interesting features buried beneath the sand in the Sahara Desert. And if you ask Charles nicely today, he might tell you some interesting stories about that. And the other thing you have to remember is this was 40 plus years ago, and they were doing these amazing radar experiments without the benefit of all the fancy electronics technology that we have today. So just being able to do that was quite a miracle. So with all the success, with especially the radar instruments on the shuttle, it's no surprise that Charles was rapidly climbing the ranks at JPL. In 1987, he was asked by JPL Director Lou Allen to join what's called the Executive Council. This is the top body at JPL that advises the director. And at the age of 40, I believe, Charles, you were the youngest member of the Executive Council for many years. And Charles was asked during this time to take charge of all of science and instruments at JPL. And so he had a rather large responsibility. And then in 2001, Charles was appointed director of JPL, succeeding Ed Stone. And during Charles's tenure, which lasted 16 years, which is, I think, longer than any other JPL director, other than Bill Pickering, who was director when NASA was created, when JPL joined NASA, and he was also director when Charles joined JPL. So Charles is the second longest serving director of JPL. JPL was extremely successful under Charles's leadership, and I think you'll be hearing today about some of the amazing successes, including landing the Spirit and Opportunity rovers on Mars, landing the much larger Curiosity rover in 2012 with the amazing Sky Crane landing, and I think Charles is going to show you some videos about that. Really just amazing. And the landing was so amazing that Charles received a congratulatory phone call from President Obama as President Obama was flying on Air Force One. So I don't think many people can say that. You probably also have heard about the rover, I'm sorry, not the rover, but the helicopter that has been flying on Mars. It's called Ingenuity. That project would not have happened without Charles's vision and leadership. He was the one that really made that happen. Well, I could go on and on talking about Charles's incredible career. He's got an amazing long list of awards that he's received. He knows all the big shots in the space business worldwide. And yes, that does include Elon Musk, for better or worse. And I could go on and on talking about Charles, but I'm sure you'd much rather hear directly from Charles himself. So please join me in giving a warm welcome to Dr. Charles Elachi, a truly legendary space pioneer. Charles?
Did I do good? Yeah. Okay. That's about the extent of my Lithuanian. Thank you, Jonas. And I want to also say that Jonas played a key role as he was the chief technologist at JPL over many years that I was director. But also Jonas and I have been friends and colleagues at Caltech for decades. First, I want to thank the organizing committee, for inviting me. And I want to thank Lucas and Ericas here, who really were kind of my host and helped me arrange all the presentation and picking me up at the airport at midnight. Ericas was able to do that. So what I'm going to do today is to kind of give you a little overview about some of the recent activity, in space exploration. But also I'm going to add an additional twist because I know there are lots of entrepreneurs and people interested in getting in space, young people. So I will talk also about how we are utilizing space and what are the opportunities that are coming up, because things have changed tremendously in the last 5 to 10 years from the early days of space exploration. So I always love to start with this picture here. This was taken by the Jim Webb telescope. That's the largest telescope built in, for space purpose. And basically this area, this picture covered an area, if you take a euro at the end of your arm, that's about the area in the sky covered by this picture. So imagine how many hundreds and hundreds of these bright spots. Each one of them is a galaxy, and each galaxy has billions of stars. And if you look at the whole sky, there are billions of these. So it's amazing when you look at the universe around us. It's amazing what the universe is made of. And basically, our purpose in space exploration is to try to understand how did that all happen. How did it start from a Big Bang about 13 billion years ago? And here, we are sitting here, you and I, kind of having this conversation. How did that happen? How did that evolve? What can we learn about it? How can we improve our life? How can we predict what's going to happen in the future in our universe? That's one of the key objectives of doing space exploration. Now, one thing interesting about this picture, you see that a number of these galaxies have like a bent light a little bit. Now, first reaction saying, oh, they have bad optics. The thing should look at single points. But in reality, this is an actual phenomena which is happening because of gravitational way of gravity bending light, which was predicted by Einstein. Basically, you are seeing galaxies which are very far away, and their light is coming toward us, but in the middle, there is kind of mass of dark matter and other galaxies, which actually bend the light, coming to us. So this is good scientific investigation happening due to this bending, of the light. So it's not a distortion. Now, let me tell you a little bit about JWST to give you a feel about the challenges usually we have, particularly on large spacecraft. So here the telescope was, I think, 6 or 8 meters, 6 meters. And the largest launch vehicle that we have can hold only 4 meters. So that's the diameter. So we had to fold the telescope. We couldn't fit it, inside the shroud, of the launch vehicle. So you see these segments that you see in here. So it was kind of folded in. And you see this shade at the bottom, which is the size of a tennis court, also was folded in. And then once we got in space, we unfolded it. Now, you say, okay, what's the big deal, unfolding this? The only problem is the telescope has to unfold and be a perfect mirror. But despite all the distortion and the change in temperature and so on, it had to be a perfect mirror. So the way it was done behind each one of these segments, actually there were actuators. And we kept adjusting, moving the actuator little by little until we got the perfect mirror. And that has to be done regularly because also there is a temperature change every once in a while. And here we are talking a fraction of micron. So you can imagine the challenge that was required. Now the shade at the bottom is because as in telescope, you have to be in the dark. In space, the sun is shining on you all the time. You cannot go under a tree, to get a shade or anything. It's always shining on you. So the shade is basically to block all the sunlight. So the telescope itself is sitting in the dark in space. And in addition, we wanted to make sure this telescope operated in the infrared at very, very low temperature that is needed for the detector and for the telescope. So we needed to have the shade also to block all the heat coming from the sun. And that's partly why it is layered, as you see here. That helps, reducing the thermal emission, which is coming from the sun. So we can get down to a few degrees absolute. So these were some of the little challenges that the people developing this have to face. And this is an amazing telescope. I would recommend when you go home, go and Google JWST best image of 2023. And you will see the amazing images that are being collected by that telescope, not only for scientific, but also for the general public, artistically speaking. So these are just a sample of some of these pictures. This is a picture of Saturn. It's not as resolved as what we have from spacecraft which fly by Saturn, but to give you an idea about the beautiful planet, picture of Jupiter. Again, to give you an idea of the size, you see that what we call the red spot, this here, that's about the size of Earth. So our whole planet can fit in that little spot. And that's Neptune, one of our kind of people start to think about future mission to it. This is a ring nebula. Again, if you have detailed questions, Jonas can answer it better than me. So that's what happened when actually at the end of a life of a star, it actually explodes, and eject all the material around it. And here you are seeing it in two different wavelengths, in the near infrared and the middle infrared. So you get different kind of information by doing effectively spectroscopy, on the nebula. And by the way, people always ask me, our sun will explode one day and destroy everything around it. But don't lose any sleep. That's about a few billion years from now. So I don't think we'll have to worry about it for a while. And these are some other example of area where stars are actually being formed. So sometimes I sit down and I spend hours looking at all these images because they have both scientific value but also artistic value. They look like great paintings. And it kind of gives you an amazing picture of what our universe looks like. Now, let me talk mostly, I'm going to be talking about our solar system. And as you can see, this is our solar system. Think of the sun way to your left. And then you see Mercury, Venus, Earth, Mars. And these are to scale. So that gives you an idea about the size of the planets, Jupiter and so on. And we are the number 3, from the left. So I usually tell people that nice little blue dot, that's all of us, all your friends, all the people you like, all the people you don't like, they're all living on that little dot, are in here. So we really have to protect it because it's a very valuable dot in our universe. And the one immediately next to it is Mars. And I'm going to spend a little time telling you about Mars and what we are doing and why we are doing it. So Mars is about 1/4 the size of Earth. So the area of the land on Mars is about the same as the land on Earth, if you don't include the ocean. It has a lot of similarity to our planet. The geology on Mars looks like the geology here on Earth. You have volcanoes, you have Grand Canyon, you have alluvial fans, you have what looks like dry rivers on the surface of Mars. It has polar caps, as you see at the bottom, which are made of carbon dioxide and water ice. It has an atmosphere, but it's only about 1% the thickness of our atmosphere, so it's much lighter, atmosphere you have on it. And we believe, based on the results we have gotten from exploration so far, that when Earth formed about 3 billion years ago, Mars formed at about the same time. And at that time, Mars was very similar to Earth. It actually had water flowing, on the surface. But then as things got colder and colder, and there are theories why did that happen, but faster than Earth. And basically the water either froze and went below the surface part of it, or because of the bombardment, because it didn't have an ozone layer, bombardment by the sun actually broke the H2O into hydrogen and oxygen. The hydrogen is very light, it evaded the atmosphere, and the oxygen actually, that's what oxidized the surface of Mars. That's why Mars looks red, because there is a lot of rust, on the surface. So the key question is, in the early days, when there was water on Mars, could have life evolved, on Mars? And if it did, what does it look like? And if it didn't, why not? Why did life evolve on Earth, but did not evolve on Mars? So that's one of the key questions that we're trying to address with our exploration. Now, some of you know, or some of you might not know, that literally for 20 years, we have had rover on Mars day in and day out operating and exploring, every day. So if you come to JPL, in the mission operation room, every day there is a group of people actually operating those rovers. And we started first with a very small rover, the one to the bottom left, called Pathfinder. And that was about the size of a shoebox. And the purpose of that rover was to learn how do you drive on another planet. Now you'll say, what's the big deal about driving this? My young brother have a little toy, which the problem is it takes 20 minutes for the signal to get to Mars and 20 minutes for the signal to come back. So you cannot joystick it. It's like trying to have a conversation with you. I say hello, and I have to wait for 20 minutes before you say back hello, and then so on. You cannot have a conversation. So we had to have a lot of autonomy in these rovers. We usually have to tell them, what do we want them to do for the next few days? And then they go and figure it out how to do it, driving around, avoiding any obstacles. If it gets stuck into the sand on Mars, it has to figure out by itself how to get out. If it cannot figure it out, it stops and says, what do I do now? And then wait until we kind of tell it what to do. Then we went to the one that you see completely to the left, that's Spirit and Opportunity. We had 2 rovers. These were the size of your desk, and they were solar powered. Then we come to the next one to the right, that's Curiosity. That's about the size of your car. And then Perseverance is the one completely to the right, which is the latest one we launched, about the same size. Now, the challenge is clearly getting them to Mars and landing them, but the other challenge is each one of these rovers, particularly the large one, are almost the equivalent of your chemistry lab here at the university. It has all the equipment that you use in your chemistry lab to analyze rock. So it has an X-ray machine, gamma ray machine, alpha particle machine. It has a very powerful laser. I know you all love lasers here because many of you work in that area. You see at the top, on the top boom, there is that circle there. That's a very powerful laser which actually zaps the rock, and we can look at what's being emitted. We have a spectrometer which analyzes the emission, from the rocks. They have an oven where we can take sample with an arm. You see the arm here to the right, to my right, where we can drill, take samples, put them in the oven, heat them, and see what's being emitted from the material. So it's literally a small chemistry lab which is operating on now, except a lot more expensive. And part of the challenge, there are 2 challenges. Number one, weight is premium in our space activity. You want things to be as light as possible, because to get a kilogram to the surface of Mars, you have to almost launch 100 kilograms from Earth. So every kilogram counts, in our business. And number 2, the total power running this rover is about 140 watts. So that's about like a light bulb. So we have to run all the instruments, run the rovers. Now we have batteries where we accumulate some of the powers, in the battery. So you have to have very efficient electronics, very lightweight, very low power electronics that you would need for these kind of missions. So let's see what. And this is what a real one looks like. I think I was mentioning to you about the high bay at JPL. So that's where we assemble spacecraft. That's one of the facilities we have to assemble it. As I told you, this is about the size of a car. You see all the people in there, they are all wearing what we call bunny suits, because they have to keep the area very, very clean, both from particles as well biologically very clean. Because the last thing we want to do is to send a rover to Mars, detect life, and we find that really it came from the people who were working on it. Somehow there were some organic material to do that. So we do a lot of cleaning, both chemical and also thermal, before we launch the spacecraft, and we preserve them very carefully, to stay clean. And the people who are working on them are, all in these bunny suits. Now, give you some illustration, if some of you are material science students here, is on Mars, the temperature during one day. The day on Mars is 24 hours and 40 minutes, approximately. During a day at noon in the summer, it's warmer than Vilnius. At night, it's much colder than Antarctica. So in 24 hours, the temperature goes up and down many hundred degrees. So you could imagine the stress that puts on the material of the body of the rover. So we avoid having any soldering. There is no soldering on it. So basically, we machine everything. So if you take the wheels, we actually take a block of aluminum and we machine it. So we don't have any soldering. The same in the box which contains the electronics. So it requires a lot of challenge of figuring out thermally how you design the rover. And then to keep the inside electronic warm, this one, I think I missed to mention to you, actually we use a small nuclear generator. So we use basically plutonium, which as the plutonium decays, we use then thermoelectric couplers to generate electricity. That's how we generate the 140 watts. Fortunately, not all the heat is being used, so the rest of the heat, we actually circulate it across the rover, through the rover to keep the inside of the rover relatively warm despite all that change in temperature. Sometimes people ask me what kind of engineers, you hire. We hire from every discipline. We need electrical engineer, mechanical engineer, physicist, laser scientist, thermal scientist, material science, almost every technical discipline. We have people who come and work on it because they have to work as a team to make all of this kind of challenging activity. So now what I'm going to show you is how actually we land these rovers, on Mars. So just imagine the rover is the one you saw earlier is sitting here at the bottom where it says rover. We had to fold it in because it's pretty big. And again, we don't have enough volume at the top of the rocket, so we have to fold it in. Then as we are arriving to Mars, we are coming at almost 60,000 kilometers per hour. And we have only 6 minutes to slow down so we can land very softly on the surface. Otherwise, we end with a crater instead of a rover on the surface. So we put a heat shield at the bottom, and that heat shield is used as we enter the atmosphere. It's basically like if you are driving at high speed and you put your arm outside, you feel the pressure. That's exactly what it does, except at much higher speed. Matter of fact, the surface of that heat shield goes up to about 2,000 degrees centigrade, from the energy which is being consumed as we enter the atmosphere. Then behind it, we have what we call the descent module. You'll see in a minute that how we use it to come and at the end to descend on the surface. Then we put a back shell. All of this, we have a parachute at the top of the back shell. It's a supersonic parachute, the largest ever built. And then we have a carrier, or what we call a cruise stage. That's a spacecraft which takes us to Mars to arrive and then drop everything below it. Now, to give you an idea, the heat shield basically, or if I take this whole spacecraft and look at the velocity and the mass and calculate 1/2 mv squared, I'm sure you all know what that is, that's the energy is in it. It's the equivalent of 18,000 race cars going at full speed. That's how much energy as we are entering. And we have those 5 minutes to dissipate all that energy. So the heat shield takes a significant amount of it, and we open the parachute to slow us even down. And as we get close to the surface, we fire the retro rocket on the descent stage. And then once we are about 20 meters above the surface, we get to zero velocity, so we hover, and then we sky crane slowly the rover down to the surface. And everything has to work perfect. If one of them doesn't work, or if one piece of the computer hicks up during this, because we have 10 to 20 minutes to communicate with it, it has to be done completely autonomously. So it's just one hiccup in it and the mission is lost. So now and you see all of them, we have a bunch of cameras. So I'm going to take you and show you exactly what was happening in the mission operation room and actually what was happening on Mars as we are deploying, all in real time, with 10 minutes delay or 15 minutes delay. So that's the Mission Control Center at JPL.
We're starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy.
So this is the 5 minutes, we call it the 5 minutes of
a better look at the ground.
Because everybody is sitting down anxious. So that's the parachute open.
Deploy.
So this
the navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration
what the colors mean,
in
why
the
do we have
velocity.
colors
Our current
on it.
velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
So now then we drop the
Heat shield set.
after we have
Perseverance
slowed down, we drop it
to
down.
subsonic
And this is
speeds,
Mars in
and
the
the heat shield has
background.
been separated.
So if
This
you are
allows
traveling to Mars,
both
that's
the radar and the
exactly what you
cameras
see.
to get their first
The color,
look at
the
the
speed
surface.
of coming
Current
down,
velocity
that's exactly
is
as if you are
145 meters
traveling
per
to Mars.
second at an altitude of about 9.5 kilometers above the surface.
Now, some of you will be wondering, why is it wobbling for two reasons? One, you are on a parachute, so that kind of as you are coming down the parachute. And number two, we wanted to land in a very specific area, so we take pictures of the surface and we keep moving the spacecraft to make sure we are centered at the area that we want to land at.
Altitude 7.4
That's all being
kilometers.
autonomously
Now has
controlled
radar lock
on
on the
board the
ground.
spacecraft.
Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
So it looks like any desert area here on Earth.
We're coming up on the initialization of terrain
Usually when I'm giving this talk like in Saudi Arabia or it looks like Saudi Arabia. I cannot say it looks like the Baltic.
At an altitude
it's very different.
of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Rhyming. TBA is nominal.
We have
so you can imagine the tension
engine.
of the people sitting down watching this. Now, one thing interesting is we are watching it and getting the signal that everything has happened 10 minutes ago. So it has already landed or crashed, and we are just sitting down and getting the signal. It's kind of a little bit funny feeling, when we are in the control center.
75 meters per second.
You can see sand dunes, which are generated because of water and wind.
TRN Safety Bravo.
Now, as we get close, you will see the retro rocket firing, and you see plumes, from the sand coming out.
30 meters per second, altitude of about 300 meters off the surface of Mars.
So now we are getting a few tens of meters from the surface.
Accordion, which means
so
we are
you see the retro rocket
the
impact on the surface.
About to conduct the sky
and you
crane
can
maneuver.
look at the two at the left, and that's when we are sky craning down. So you see we are sky craning the rover down, and the other picture looking up for the descent module. And then once we feel touching the surface, we cut the cord, and the upper part goes away, and the rover is sitting on Mars.
MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
Now, there are a couple of reasons for the excitement. Number one, you are landing on another planet. Number two, these people have been working on this mission for anywhere between 8 and 10 years, and everything depends on those few minutes. Either you have a great success or your 8 years of work is completely gone. None of that happened. Now, I mentioned to you earlier, I'll tell you what's the color on that parachute. That is a digital code which shows the longitude and latitude of JPL. So if somebody gets a parachute, sometimes they know exactly where it came from. Now, on the latest rover, as Jonas mentioned, we added a little helicopter. Now, again, you'll say, what's the big deal? You have drones everywhere, in here. The challenge, as I told you, the pressure on the surface of Mars is 1% the pressure on Earth. So that's like flying a helicopter at 30,000 meters. There has never been a helicopter flown at that altitude. That's higher than when you travel from here to the US altitude-wise. So it was a huge challenge building a helicopter which can operate at that altitude. So the whole helicopter had to be done within 1.5 kilograms. All the electronics, everything on it, the blades, everything had to be on 1.5 kilograms. And that's not the only challenge. The other challenge, again, because we have the time delay, the helicopter had to be smart enough of when it's coming to land. That was our biggest, it takes off and then come down to land. It has to look at the surface and avoid any rocks or anything, because otherwise, if it hits a rock, it will tilt. And the whole helicopter is about this big. So it had to have enough intelligence in it and computing power to be able to avoid any obstacle, on the surface. So we were very nervous about it, And that was one of the flights. This is the third one. On the first one, we were really nervous. But as we were getting, so we got a little bit better on doing it. So you can see it in the bottom left. It actually takes off. That's the first time ever we fly on another planet. So that is like the Wright brothers 100 years later, flying on another planet. And then we were doing all kinds of tests, to see how flexible it is, what we can do. And because we were nervous about it, we promised NASA that we'll do 5 flights. And if we do 5 flights, we declare success. Well, we ended doing like 75, flight. It worked so well. And the other interesting thing here, because we came with the idea of it halfway through the project, so we didn't have enough time, to build it in the traditional process. Most of the electronic on it was commercial electronics. But it was very carefully chosen, to do that. I mean, we qualified it, we tested it and tested it. So we didn't have the time to actually use what we call flight hardware, for that purpose. But it worked great, and you saw it coming back and landing. And the advantage of a helicopter, it gives you a much farther reach than the rovers. The rover is good, you can build a lot of electronics in it, a lot of instrument, but it has a limited range. And then you cannot take it like inside a canyon, because the risk of damaging it. The helicopter will allow you to reach significantly bigger distances. And also we use it as a scout. So it used to go ahead of the rover, explore areas and say, oh, that's some area interesting. And then it guided the rover to actually do that. So now the next big step that we're working on is to actually bring samples back. So this rover, the one on Mars now, has been going around collecting samples. And when I say sample is about the size of your finger. And then we drill, take the sample, put them inside a tube, and we had to seal the tube. And that's all being done autonomously. And then the idea is to be able to go in the future, collect all these samples that the rover has collected, and then bring them back to Earth. And the way we're doing it, or we're planning to do it, is we send a lander, you can see on the right in here, and then the lander has a rocket, and then we'll have a helicopter which will fly, collect the different samples, bring them back, put them in the nose of the rocket, launch the rocket in orbit, have the sample capsule go in orbit, then have a spacecraft rendezvous with it and bring the sample back. Piece of cake. Very easy. It's a good challenge for good engineers. Now, we are having challenges in this mission. If you keep track of what's happening in the US because of budget situation, we are re-reviewing the architecture, and then we are kind of thinking about how can we streamline and reduce the cost, for the mission. So unfortunately, it will be delayed. Originally, we were hoping to launch it in 2026. Probably it will be more late in this decade. And there are opportunities for you to participate because ESA is a partner with us. And I know Lithuania is part of the European Space Agency. Matter of fact, that spacecraft at the top left, which will go rendezvous to bring the capsule back, is actually being developed by the European Space Agency. Let's see what else I have on this one. I think that's. Now, let me tell you of a different kind of mission also what we're doing. And it's a mission to go to Europa. Europa is a satellite of Jupiter. It's bigger than our moon. And you'll see in a minute why it's interesting. And that's a spacecraft being assembled again in our facility at JPL. It's the largest spacecraft ever built that we had. It had like 12 or 14 instruments on it, including instruments from Europe on doing that. And this mission will be launched basically October of this year. So we are at the final stage of actually testing it and verifying it. Now, the reason is interesting. That's a picture of Europa taken from one of our previous missions. It turned out Europa is made of ice, H2O ice. And then you see all these cracks, on it, and you see this orange material. This is organic material. And what we believe, if you look at more the detail, on it, you see what looks like all the fracturing on the surface. It looks very much like, if you look between this image and this image, it looks very much as when you fly over the North Pole and you see the ice flows, over the North Pole. So we believe that this ice that we see is actually floating on an ocean of H2O just below it. And the size of these ice flows are typically here. It's a reference for people who know the Los Angeles area. Between the Los Angeles airport and where JPL is, that distance straight line is about maybe 30, 40 kilometers. So these ice flows are typically anywhere between few kilometers to about 10-kilometer size. Because they are so small, that's an indication that the ice thickness is not very large. Otherwise you wouldn't have these pieces of ice floating on it. So now when you put one and one together, so you have an ocean below the surface, it's made of H2O, you have organic material. So the immediate next question is, could there be life in that ocean? On it, could have life evolved. It has all the ingredients that lead to life at the bottom of our ocean. When you go deep in our ocean where there are vents and heat, so you don't need the sun. When I was a student, I was educated that in biology, you need the sun to be able to have life evolve. Well, it turned out you really need energy, not the sun, because at the bottom of the ocean, we actually get a lot of life, even there is no. So for this mission, one of the objectives is to fly by Europa and sound the ice using a radar instrument to see how thick the ice is, because in the future, we want to put a lander on the surface, drill our way through that ice, and put a submarine in the ocean to get that another piece of cake, another challenging engineering job. So as I said, this mission will be launched in October. It will take about 6 years to get to Jupiter. Again, that's one additional thing. I mentioned it earlier. You have to be very patient in this business. It typically takes anywhere from 6 to 8 years to develop. Well, first it takes a dozen years to convince Congress in the US to fund these missions, because these are not cheap missions. And then it takes about 6 to 8 years from the design to develop it. And then depending where you are going, Mars is about 6 to 9 months. Going to Jupiter is about like 5 to 6 years. Going to Saturn is like 10 years. So you have to be very patient, in working these exploration. The side benefit of it is good job security, because you have to stay on the project for all these years. Let me mention to you another interesting mission, and there is a reason I want to mention it here. This mission called Psyche is on its way to one of the asteroids, which is called Psyche. It turned out between Mars and Jupiter, there is a series of asteroids, literally thousands of asteroids, chunks of rocks of different sizes. One of the largest one is Psyche, and the unique thing, it's about 100 kilometers. So it's a pretty big chunk. And the unique feature about it is that it's made completely of metal, versus rock, which is most of the other one. And we do that from spectroscopy from the ground. So the intent will be the spacecraft to go and rendezvous, with it and be able to analyze it in detail and understand it. One thing of interest to you here a little bit is on this mission, we are doing our first attempt to actually use laser link as communication. So we have a radio link, but also we're using a laser link, and we're demonstrating it as a technology. And I think Ericus will appreciate one thing. The first image we sent down about a month ago was one of the operator, he had a video of his cat. Ericus was telling us yesterday how much he loves cats, and he was showing me and my wife his cat. So that was the first image transmitted with a laser, was a video of a cat, coming down, and it was very successful. And on the ground, it was received at the Mount Palomar telescopes that Jonas used to be the head of that activity. I think he talked about it last year when he was in here. So the idea is what we try to do on every mission is to put at least one technology experiment to demonstrate something new, to evolve our capability. Because in general, we tend to be pretty conservative, on this, because they have to work. Once you launch it, you cannot bring it back to the garage and fix something. So it has to work. I mean, software we can always upgrade, but the hardware is pretty fixed. So we tend to be on the conservative side in the technology, but to be able to move the technology, we put at least one new technology experiment which is redundant. So in this case, we have a microwave link, but also we added the laser link to demonstrate it. And now that it's demonstrated, probably it will be more common to be used, in the future. So that's an artist's conception of this. Now, let me bring you down to Earth here. One of the missions that we are launching again in September is what's called NISAR for NASA Astrosynthetic Aperture Radar. As Jonas said, that was my technical background. So what the radar does, to give you an idea, that dish that you see at the top is about 20 meters in size. Again, we have to deploy it. But what basically the radar does, synthetic aperture radar, is it does images exactly like regular photography, except it uses microwave instead of using visible light or infrared light. So it has a couple of unique features. Number one, because we use microwave, it doesn't matter if it's cloudy or not. The signal penetrates through the clouds. Similar, your radio and TV work irrelevant if it's cloudy or not. So you can take images all the time. Number two, because you are using you are generating the signal, because the radar actually generates signal like the policeman who try to catch you speeding. We don't rely on the sun. So it doesn't matter if it's day or night, we can get images. So we get images all the time. And you see these, I showed two pictures here. The one at the top, they were taken over Egypt. The one at the top is actually a camera, it's a photographic image taken from the shuttle. The one at the bottom is the radar image. And if you look carefully, you see a lot of similar features, like where the Nile is. But where you see the dunes at the top, actually you see the drainage channel of where the Nile used to be, before many thousand years ago, and then it got covered by sand, and actually we're seeing through the sand. That's what Jonas was mentioning it. So that's what made it dramatic public thing, particularly in the area of archaeology and paleontology, that you actually can see what's being covered by sand down to many meters, below the surface. So that led to a lot of exciting, application, for this kind of instrument. And then you can do also colored photography with it. The same way you see color with your eyes because you are sensitive to a couple of wavelengths. Here you can do the same thing. You can use different wavelengths in the microwave and give each wavelength a different color, and you can get color photography using the radar, and it gives you different kind of information about what you are looking at. So the reason I want to show you this is because look at this one. This is Los Angeles. And what we are seeing is the surface change over Los Angeles over a period of 6 years. And look at the scale. We're talking about few centimeter change in the surface. So actually Los Angeles is moving up and down on it. And the same thing is happening in Vilnius. You might not feel it, but Vilnius is moving up and down. And the reason it's moving that every time you pump water from the aquifer, the surface subsides a little bit. And every time it rains, or in our case, we get snow in the mountain and it fills up, the surface moves up, a little bit. So in a sense, we are sensing what's happening below the surface, in the aquifer by looking at the surface change down to a fraction of a centimeter. And that's a technique that we call interferometry. Similar to the Fresnel interferometry that you use in your lab here, the basic concept is the same. And by looking at different times, over a long time, we can see the surface change. And not only because of water table, but like we're doing a project in Saudi Arabia about how much oil is being pumped from the subsurface. If there are earthquakes, surface will move. You can measure that. If you are building infrastructure, the surface will subside a little bit. You can measure that. And that shows you one example for the earthquake over Turkey, which happened about a year and a half ago, where you see these fringes, and every time you go from one fringe to the next, that means the surface moved a couple of centimeters. So actually, we're getting a picture of the earthquake, itself, which gives you the pattern, of how that earthquake happened. And also, it has the other benefit where the fringes are very close. That means there was a lot of motion. And we usually send that information to the rescuer very quickly, because that's most likely where most of the damage have happened in that area. So that gives you an illustration of some of these applications. And many of these, when I started, we didn't even think of them. All of these have developed over the last decade. And this mission is going to cover, the one that we'll be launching, will be covering the whole Earth literally every 6 days. Every 12 days descending and every 12 days ascending. So you'll have a map of the Baltic states every 6 days at a resolution of about 10 meter and surface change down to fraction of a centimeter. So if the trees grow, if you are interested in the growth of the trees, we can measure how much growth that is happening. If the soil subsides for whatever reason, after it's freezing and it melts, we actually can map, that change. So that gives you illustration of the kind of capabilities that will be available. And by the way, on all US and ESA mission, the data is free. So once we start getting the data, you can get an account, free account, and you can access any data you want, and you can actually analyze it and use it for your purpose. And by the way, the same kind of radar techniques we have used on Titan, on the Cassini mission, which finished a couple of years ago. And that's how we discovered that actually there are lakes on Titan. Except the difference is the lakes are made of methane because Titan is so cold that water freezes, so the rocks are made of H2O, but the liquid, the rivers and the rain and the lakes are made of methane. Kind of an interesting environment. Let me move to other kind of things we are doing in Earth observation is actually using imaging spectroscopy, the same way I see you have a lot of work on spectroscopy here. Imaging spectroscopy is actually using a spectrometer to get images at different wavelengths. So what we get is what we call in a spectroscopy cube. That means we take a picture and then we take a series of pictures at slightly different wavelengths. So we have a stack in this case of about like 250, images at slightly different wavelengths ranging from 500 nanometer to 2500. And then if you look at one pixel and go through the pixel, you get a spectrum of that pixel. That's what I see on the right. And it turned out, as I'm sure many of you working in the field, spectroscopy is like fingerprints. Every material has a very specific spectrum. The same way if every one of you have a different fingerprint on it. So in a sense, from space, we can tell you exactly what's the composition of every pixel, on our planet. And it has a wide variety of application, be it in geology or in agriculture. And it turned out, interesting enough, like if you have a field and if it's dried or trees which are dry, they have a slightly different signature than if they are, have been irrigated. So people are starting to use it about how to control irrigation in a practical manner. And this was taken from an instrument we have on the space station. And one interesting thing which we are using it for now is to monitor emission of methane. As you know, methane is one of the key greenhouse gases. Matter of fact, we talk a lot about carbon dioxide. Methane is 100 times more potent as a greenhouse than carbon dioxide. There is not as much of it. That's why you don't hear about it as much, but it's have much more impact on our environment. So this actually shows emission from a landfill outside of Riyadh, and we are seeing area where there is also emission coming from oil facilities. So this will allow us to both monitor, the methane emission and make sure either we inform or enforce, the rules about the emission in the environment. And this experiment, unfortunately, it's on the space station, so it doesn't go as far as Lithuania. But it covers most of the tropical region between plus minus, 50 degrees. Now, when I showed you all these big spacecraft that I mentioned earlier, one of the big advances which have happened in the last decade is the miniaturization of electronics. And that's enabling to actually build spacecraft that I could have brought in my luggage, to bring it to here. I don't know what the customer would have wondered what that is, but literally they are about that size, that spacecraft, and they are very capable. Just to give you an idea, this spacecraft, we use it to actually as a relay from Mars to Earth. On one of the landing missions, we were landing on the other side of Mars, so we couldn't see directly from the lander to Earth. So we built a small spacecraft which came at much higher altitude. It could see the back of Mars and sees Earth, and it was a relay. And it was all done, literally for, I don't remember the exact number, for less than $10 million, was built in like 2 years, and actually was completely successful. And I love this other picture. That's the one scientist carrying his spacecraft, with him. So that was for an Earth orbiting spacecraft. And actually, it was a passive microwave, instrument to monitor precipitation in the atmosphere. The reason I wanted to show you this is that a university like Vilnius or small companies here in Italy, you actually can build your own spacecraft. And some of you are starting to do that. And these are not toys. These are actually significant value, either commercial or scientific, that you can do that. And now a number of universities in the US have programs to actually have student building spacecraft, as part of their education. In this case, that shows actually the amount of water in the clouds. That was with the instrument I showed to you earlier. And on the commercial segment, the fact that we can build them so small, that means we can build them relatively cheap. And now a number of companies are building a network of these spacecraft to use for telecommunication or Earth monitoring. So the whole idea, some of you know that companies like SpaceX or Blue Origin are building network of satellite that can communicate directly with your iPhone. So then you don't need any towers. So wherever you are, you actually can communicate with one of the satellites. And these are being built effectively like production. I went to one of the facility at Blue Origin doing that, and it was like you have a production of cars, you have production of small spacecraft, of this size that are being built. So this is going to be a key element of our day-to-day life. Now, one thing I always love to ask people, and you are smart here, so probably you know that. How many of you have used space in the last couple of days? Very good, most of you. Because every time you are driving and you are looking at the map, you are actually using the GPS, network. And one thing I learned, every time you go to your ATM machine to pull money, you are using spacecraft because the clocks are synchronized through the spacecraft. The clocks would be in the bank and your ATM machine. So it's becoming like part of our life. We don't think about it, but it's becoming part of our life of actually utilizing space. So that creates a lot of opportunity, commercial opportunities, for companies to do. Every time you look at the weather, you're actually using satellite. To tell you, I have this kind of story. It sounds like a joke, but it's a real story. A NASA administrator was testifying in Congress, and one of the congressmen was telling him, I don't understand why we spend all this money on these weather satellites. If I want to know the weather, I can go and Google it, and I find the weather on doing that. So the administrator have to nicely tell him, not to tell him, hey, dummy, what is this? But to tell him, well, but we're using spacecraft to get that part. So and in a sense, it's a two-sided story. On one side, it shows how less smart are the politicians. But the other side is becoming so much part of our life that we don't think about it, about that, what we are doing. And the other thing where you are going to be seeing a lot of development is this network of satellite to actually monitor our environment. Again, if you are interested, go and Google Eyes on Earth, like your eyes on Earth, JPL, and it will show you every satellite we have in Earth's orbit, where it is. You can track it. You can get the data coming from it, like you are seeing here, data about moisture, soil moisture, and it's data which was taken a few hours ago. So in the future, you are going to have a series of these networks where it tell you in real time on your iPhone, actually what's happening in our environment worldwide. Matter of fact, a number of companies are starting to do that for weather purposes and precipitation purpose. Now, if you leap forward a little bit, you are going to be seeing more tourism, happening. This was because recently, so I picked this one, where actually, if you have enough money, you can actually travel to space, as a tourist. And if you look maybe 5 years from now, a number of companies are actually building commercial space stations. And the way they are using them is a little bit like the mall where you go shopping. So the companies will build the space station, and you can rent space on it. Like in the mall, a shop will rent space. So you can say, hey, I want about 100 square feet for 6 months, and there will be a price, and the company actually facilitates the travel to it and coming back and the power, and then you can do your experiment, be it scientific or tourism. So that's going to become a common thing over the next decade. And if you think even further than that, the same thing is going to happen on the moon. Whereas we're having station on the moon, you can do scientific or touristic, activity on there. And let me close by a couple of examples, because sometimes people say, okay, are there any other technologies that we benefited from space? Almost all of you, if not every one of you, have an iPhone. And you wouldn't buy an iPhone if it doesn't have a camera, on it. But not many people know that the technology behind that camera, it was not invented at JPL, but people at JPL actually worked on, miniaturizing it for low power and low weight. And it was done for telescopes and scientific instruments like what Jonas does. We didn't think about using it into a camera, but an entrepreneur said, oh, I can use that into a camera. So they actually took that technology and have been using it for commercial purposes. All these rovers I showed you have an arm. So all the technology for articulating and manipulating them, we developed it about 20 years ago. Well, that's what's being used now in robots, be it for rescue or be it for surgery. So that's another example of technologies that we developed for space. And we didn't, I'll be candid, we didn't develop it for application because we were doing scientific activity, but then some smart people figured out how to do it, how to use it. And I love this example for this. Many of you watch cartoons or play games, but I don't think any of you would know the name of a Jim Blinn. You can go and Google it. So Jim Blinn, about 30 years ago, was working at JPL. And he was working on animation to visualize spacecraft as they fly, by a planet. And then that technology picked up, and that's what's being used now in software, animation on doing that. So that shows how, investment in science and technology, irrelevant what's the purpose of it, actually will lead to benefit. And that's a message I always like to give, particularly for countries like Lithuania and so on. You don't have to ask what it's going to be used for. I think the government should invest in doing education and technology, because any gain of knowledge or any gain of new capability, some smart person will figure out how to use it on a commercial basis. So that's what we use our logo at JPL and Caltech, to their mighty things. And what we mean by it, and that's a quote from President Roosevelt, who was 100 years ago. What we mean is don't try to do the easy stuff. Try to do the challenging thing, because that's how you push the state of knowledge, the state of technology. And you most likely will fail, multiple times. We crashed some spacecraft on Mars. I don't show them in my presentation, but we did crash a couple of spacecraft in the late 90s. But we learned from it. That's how we were able to advance the capability of the landing, and then we have been successful for 25 years of doing that. So my message to you, go and try the most complicated experiment, and if they don't work the first time, hopefully your advisor will say, that's great, I'm glad that you failed, because you are learning something from what you have done. Again, thank you very much, and it has been a pleasure being here.
Thank you, Charles. Your last comment reminds me of an evening that Vilja and I spent at JPL in 1999. It was a very long evening, and the Mars Polar Lander didn't land. It was a very sad day. And one thing I'll say about Charles is that when he became director, the spacecraft never crashed. So thank you for that. Questions?
Thank you so much for this extremely fascinating talk. I'm curious, so you said in the Mars mission, the next milestone will be bringing back samples to Earth. I'm curious, how much of that testing can we already do on Mars, and how much potential is there to miniaturize the analytical techniques and diagnostic tools that we can do in space?
The material we bring back is some
No. I'm curious, how much of the testing can we already do in space? Like, how much potential is there to actually develop new diagnostic tools that we can run in space instead of bringing the samples back? And where do you think this will go in the future? So I'm a chemist, so I'm more interested, like, how much other scientists can contribute to actually doing things directly in space. Like, is there room for potential to develop new diagnostics tests that we could maybe run on Mars instead of bringing the samples back?
Well, let me ask it in general, and I think it addresses your question. Now, the amount of sample we'll bring in maybe like 30 samples. Each sample, as I said, is about the size of your finger. And then there is a concern about what if there is some life material in it. So the samples will be brought to a facility in Johnson Space Center, which are used for really high protection facilities, like Ebola and all of these things that I'm not familiar with. And then after they make sure that they are safe, then the sample will be distributed worldwide. So if you are interested, you can apply, to get part of the sample. And basically, when you say part of the sample, you'll get maybe a little piece. And then people around the world will be analyzing, to do that. And the other part, we will not distribute all of it because technology keep evolving. So we will actually be leaving a number of them conserved for future kind of generations. So it's going to be a wide, international effort to actually do that. And there will be a protocol and a process how to do that. Now, as I said earlier, we were hoping to be able to bring the samples by the end of this decade. Now, most likely it will be the middle of the next decade. Now, one other question people ask me also, not exactly what you asked for, is how much does this cost, to do this thing? How much does a rover mission cost? And because I deal with politicians, I have to be very careful, and the public, I have to be careful, but I want to be truthful. So usually I tell them the rover that we send to Mars cost 1 hamburger per American citizen. And first reaction, wow, this is great, that's cheap, that's what I want to do. But then you can do the math, you take 300 million American with $10, so that's 3 billion, that's what the cost of the mission. So it's true, but depending how do you present it to them. If I would have said 3 billion, they say, it's so expensive. So you have to put it in the context of people, things that they are familiar with, on doing that.
Thank you for an amazing talk and mentioning the cats and lasers. But I wanted to ask about the materials used for rovers. You mentioned that they need to withstand the huge temperature changes, right? And I assume there are not a lot of materials you can use who are sturdy enough to withstand the travel, to withstand the temperature changes. So what kind of materials are used for these kind of spacecraft?
Now, for the body of the rover, again, I'm not an expert in it. I was just a director, so I didn't know this. They use mostly aluminum. Now, I don't understand the property of aluminum in detail, but that's what's being used in most of this. We actually bring blocks of aluminum because I went to the machine shop and they carve it. Now, the heat shield, it's some special kind of carbon fibers which can sustain, the high temperature. And it's the same one that's used for capsule when astronauts come back, to Earth. It's the same kind of technology. Look, if you go and Google, Curiosity or something, what materials they're made of, all the data, you'll find it on our website.
Thank you for the amazing talk. I would like to inquire on, is there any plan to make this Mars mission based on the helicopters only? Because they, as you said, can cover bigger distance, perhaps more interesting environments could be explored, and I don't know, something interesting.
Yeah, now that we have demonstrated that we can fly a helicopter, there are lots of ideas coming up about missions using the helicopters to do that. So people are thinking of networks of helicopters to fly and explore. And matter of fact, as we speak, we are looking at a helicopter which is about 20 kilogram in size, which requires a lot bigger blades and light material. So we can put scientific instrument on it. This helicopter, the one I showed you, had only a camera. on it. And I think it measured temperature and pressure on doing that. So yeah, there are lots of people thinking of concepts, to use helicopter in Mars exploration. And as you could imagine, you can take a helicopter down a canyon. You can look at the layering in the canyon as you are, going up and down. So it's going to open a whole new possibility, for exploration. Unfortunately, many planets don't have, an atmosphere, so we cannot use it on some of the satellites like Europa or some of the other. Oh, I should have said, now you triggered the thought. Matter of fact, there is a mission now being in early development to send a helicopter to Titan, which is a satellite of Saturn. The one I showed you is the lakes in it. So there will be, and that one has an atmosphere about the same pressure as our atmosphere. So that will make it somewhat easier to actually build a helicopter for it. So that would be, I think, launched in 28, and we'll get there in 34.
And what about Venus?
Sorry.
And what about Venus? It has quite a dense atmosphere. Are there any plans to explore it?
Sorry?
About Venus, the planet.
Oh, Venus? Mm-hmm. Well, Venus has a different challenge. Yes, it has, matter of fact, a very heavy atmosphere. The challenge is if you get close to the surface, you are talking about temperature in the 800 degrees centigrade. So there the challenge is different. The flying is easy, but sustaining that kind of temperature for electronic is the challenge. Matter of fact, one idea about bringing samples from Venus, because we cannot go land down and sit down for a month and grab samples, is to land very quickly, grab a sample, and then move back up into a higher atmosphere and float at the altitude where the temperature is easier to do. So, I mean, that's a kind of fun things to do in these missions, is coming up with imaginative ideas, to address a different environment that we have on these different planets.
Thank you.
Any further questions? If not, I would like to close with a small little connection to Lithuania. Charles mentioned several times about the atmosphere on Mars being very thin. He said about 1%. That makes it incredibly difficult to land on Mars. It makes it incredibly difficult to fly the helicopter on Mars. But the fact that the atmosphere is this roughly 1%, was first measured, you could say reliably, in 1965. And it was a JPL mission that did that, called Mariner 4. It was the first spacecraft to fly by Mars. And there was an experiment, the radio science experiment, that sent the radio signal through the atmosphere of Mars and looked at the time delay of the radio signal traveling through the atmosphere to determine how much atmosphere there was, and to get to this answer of 1% that you need to know if you're going to try to land on Mars. The principal investigator of that science experiment, the radio science experiment, was a Lithuanian American by the name of Arvydas Kliori, who Charles, I think, knew at JPL. So, Charles, thank you. I don't know if you want to say anything about that.
Yeah, I forgot to mention one thing. I mean, you have, I'm not sure who have, I mean, the organizer have my presentation. Anybody wants a copy of it, that's fine with me. I mean, it's public, the video and so on. It's public domain, so that's fine.